All right, in this question, we're asked to use separation of variables to find the general solution to this differential equation up here. And so it goes like this. I can write in Leibniz notation that it's dy dx equals xy. Then I separate the x and y dependence on the left and right hand sides. So I get dy over y is equal to x dx. Then I integrate both sides, and I get dy over y integral is the integral of x dx. And integrating, I get natural log absolute value of y is equal to 1/2 x squared plus c. That gives me absolute value of y. So I'm turning around the log, which implicitly has a base of e, turning it into an exponential equation instead. So absolute value of y equals e to the 1/2 x squared plus c. Now I can pull the constant out in front, e to the c, e to the 1/2 x squared. But e to some arbitrary constant is just some new arbitrary constant. So I get c e to the 1/2 x squared. Now, the absolute value of y, if y is positive, it leaves it alone. If y is negative, it multiplies by -1. So y is equal to plus or minus this arbitrary constant, e to the 1/2 x squared. So I wanted to point out here that back here when we wrote e to the c as an arbitrary constant c, that automatically implied we were talking about a positive value of c, but now I have a plus or minus a positive number c, so y is allowed to be negative. So I can just say that y is equal to some arbitrary constant that could be positive or negative times e to the 1/2 x squared. So there's our general solution. Note that the general solution comes with one arbitrary constant because the original equation was first order. All right, let's apply this initial condition, y of 0 equals 1, and get a particular solution. So when x is 0, y is 1. Plug in 1 for y. When x is 0, e to the 1/2 times 0 squared, that's e to the 0, and e to the 0 is 1. So I end up with c equals 1, which means my particular solution, yp of x, is just e to the 1/2 x squared. Finally, we're going to plot the particular solution along with the family of curves from the general solution. And in addition to that, I'm going to include the point that served as an initial condition here. And that point was 0, 1. Okay, here's our family of curves representing many values of c, each one corresponding to a new particular solution. And when we insisted that our particular solution had to pass through the point 0, 1, we selected one of those curves from the whole family and got our particular solution.